All right. Hello, everybody, both physical and virtual. Thank you all for attending this first hybrid colloquium talk. I'm pleased to welcome back Dr. Natalie Butterfield, who's joining us this week from her new position at Villanova. And she'll be talking with us today about her studies on molecular gas in the Milky Way. So, welcome.
Great, thank you.
And I'll leave it to you.
Okay, great, thanks. All right, yeah, so for my talk today, I'm going to be discussing the molecular gas that's in the inner regions of the Milky Way galaxy. So to start off, I'd like to motivate why we want to study the Milky Way galaxy in general, compared to looking at external galaxies where you can see some of these much larger features. So one of the important things that you need to understand about gas transport in the inner regions of the Milky Way galaxy is that it can affect the star formation and the evolution of these galaxies. So for example, in the top figure that I'm showing here of NGC 1300, you can see that this is a barred spiral galaxy, so you can see the nice spiral arms that are coming off of the bar, and you can see that the bar is feeding material into the central molecular zone. Now in the bottom figure of Messier 82, you can see these large outflows that are stemming from the inner regions of the Milky Way galaxy. So you can see that as gas is being transported across the inner regions of galaxies, that they can have an influence on both star formation and the evolution and structures of these galaxies as well. And I'd like to point out that these are both Hubble images, three-color Hubble images of these external galaxies. However, the distances to these external galaxies makes resolving individual clouds very challenging. As you can see here, you have a lot of the big structures that are observed, but it's really hard to identify clumps and cores within these molecular clouds on the subparsec size scales. And so that's one of the main reasons why we like to study gas in the Milky Way galaxy itself, is that we can actually resolve these clouds with high spatial resolution down to the subparsec size scales and really get an understanding of the processes that are going on within these clouds. All right, so the main focus of my talk today is going to be about the gas transport across the inner regions of the Milky Way galaxy. So I'd like to highlight what the cycle of gas is across the galaxy in general. So I have here a schematic showing how gas is being transported. So first, you get gas that is flowing into the CMZ via those galactic bar-dust lanes that we saw in the previous slide. So you get gas that is flowing in into the CMZ, and then you have gas swirling around in this almost twisted ring-like structure in the inner regions of the Milky Way galaxy, in the CMZ. And those are causing intense star formation, and these intense energetic events can blow material out, filling what is known as the Fermi bubble. And so as gas is flowing into the Fermi bubble and into the galactic halo, it cools and then rains back down to the galactic disk, thereby enriching the ISM, and then you repeat the cycle again. So you get this transport of gas across the inner regions of the galaxy that can influence the structure and star formation rates within the galaxy itself. Now, as I was showing this figure, wanted to say that these features are not drawn to scale. This is basically just a very simple schematic. These structures can vary widely in their size scales. And as it stands right here, I was showing this to Larry Morgan yesterday, who said it reminded him of Mars Attacks, the Martian from Mars Attacks. And so I'd like to stress that these are not the same size scales, and these features are not to scale. So since this is a colloquium, I wanted to discuss what are these size scales? What are these physical size scales that we're looking at for these different features? All right, so let's start with the biggest features themselves. So these are the Fermi bubbles. So they are bimodal lobes that extend above and below the galactic plane. So you can see the galactic plane extending here in the galactic coordinates, where the galactic center is located right here at 0. And so you can see above and below, get these large regions that are known as the Fermi bubbles. All right, so to put this back into the schematic that I was showing earlier, you can see just how large the Fermi bubbles are relative to gas that is in the galactic bar and in the central molecular zone, which is very tiny right here at the very center. And now even these are slightly enhanced just to show where they're located. In reality, they're much smaller than this in general. So typically the galactic bar is about 10 degrees, whereas the galactic center is only about 1 degree. And so you can see that these are still enhanced relative to the Fermi bubbles, but I just wanted to show where they were located relative to that. So now let's zoom in a little bit further. And so we're going to zoom in on the inner 20 degrees or so right about in here. And so there we see something that looks like this. So this is a nice figure that was shown in DiToro 2020, where he was highlighting some of the CO observations that they had towards two clouds. So all of these dots that you see that are inside the Fermi bubble, which is highlighted here by these dashed lines, all of these are known as H1 clouds. And they've been studied by Jay Lockman and Naomi Clark-Griffiths has some papers on those. So you can see that relative to the large size scale of the Fermi bubbles, you get the gas that is flowing in from the galactic bar into the CMZ on both sides of the galactic bar dust lanes here. Now, they mentioned that I tried to draw these figures as close to what they physically look like in the sky. And so just to kind of show you what the, an observation of gas that is in the Fermi bubble where you have, or in the galactic bar dust lanes, where you have gas that's shown here in blue as being on the near side, gas that's in red is on the far side. So the schematics are fairly similar. Try to get them as close as possible just to make it easier to understand. All right, so for the first part of my talk, I want to focus mostly on the galactic bar dust lanes, since that's what most of my current research has been on in the last year or so. All right, so identifying gas that's associated with the bar. So identifying gas that's towards the galactic bar is really challenging. You have to look through a lot of material in the galactic plane in order to see into the galactic center. So this is just an artist's rendition of what the Milky Way galaxy might look like. Again, we cannot go above the Milky Way galaxy to see this. But based on observations, we have an idea of where the spiral arms are roughly located, where the galactic center is located. And so the Milky Way galaxy might look something like this. So there's a lot of material that you have to look through. So how do you identify gas that is associated with the galactic center and not with one of the spiral arms? So to do that, you do what's known as a position velocity diagram in order to identify features that are associated with features of interest, whether or not you're looking at a spiral arm or if you're looking at the galactic center, you can use position velocity information to identify those features. And so that's what's being shown here. So the top, you can see the image of the galactic bar dust lanes that I had shown earlier. So this is plane of sky. This is what we see when we look out and we observe towards the center of the galaxy. But if you look at the third dimension, which is velocity, and that's what's shown here on the y-axis. So if you look at this as position velocity, you can see that these features really stand out in position velocity space. So you have the near side of the dust lane, and you have the far side of the dust lane really striking in this position velocity diagram. So how does this tell us, though, what the structure of the gas is doing in the center region? How does this tell us the physical location of some of these clouds and their orientation? Well, to do that, you have to do a 3D geometry of the clouds relative to the position of the sun. So in this figure here by Sormani and Barnes, 2019, they basically recreated what the structure of the gas is doing in the galactic bar dust lanes. So here they are assuming the angle between the orientation or direction of the bar relative to the sun is 20 degrees. And so this is based on gas dynamical modeling along with star counts and near infrared photometry. They also assumed in this figure that the dust lanes are stationary relative to the rotating frame of the bar, and that the bar itself is a rigid rotator, rotating about 40 kilometers per second per kiloparsec. So based on the orientation and geometry of these structures, they get an idea of how the bar is oriented relative to where we are located at the sun, which is about negative 8.2 or so kiloparsecs away from the galactic center itself, which is shown here as this black circle. Okay, so that's essentially how they go through and they identify the structure of the galactic bar. But to put this into a schematic that's a little bit easier to digest, the galactic center might look something like this, where you have your galactic center, you have the gas that's associated with the galactic bar dust lanes that's accreting into the inner regions of the galaxy. So to relate this to the figure that's shown on the right, you have something that looks like this. So you have the near side dust lane, so that's shown here in blue, and that's accreting into the galactic center, so it is moving away from us, which is why we see positive velocities. You have gas on the far side of the dust lanes that are accreting again into the galactic center, but they are transversing the bar towards the sun, and so therefore you're seeing these negative velocities. So the galactic center might look something like this if you could observe it from the top down. Now, one of the other things that I wanted to mention, because I will be discussing or mentioning these throughout the rest of my talk, are the X1 and X2 orbits. So these are the inner limboid resonances for gas that's orbiting in the galactic center. So the X1 orbit is parallel with the galactic bar, so that's gas that's associated with the dust lanes. So any of that gas is associated with the X1 orbits. Now the X2 orbits are perpendicular to the galactic bar, and typically any gas that is associated with the X2 orbits is gas that is thought to be in the central molecular zone, or CMZ. All right, so if you hear me say X1 orbits or X2 orbits, this is what I'm referring to. So again, X1 is parallel to the bar, so that's this larger structure. X2 is the smaller structure, and that's perpendicular to the bar. Okay, so now I would like to highlight some recent work, GBT work, on the galactic bar dust lanes. So we recently had 2 pilot studies targeting 2 regions in the galactic bar dust lanes using the GBT. So these were targeting mainly the lower transitions of ammonia. So these are the non-metastable 1,1 through 3,3 transitions. Mainly, the main reason why we wanted to target these using the ammonia molecule is because the ammonia molecule really traces a lot of the dense gas in this region. That's what we were looking for, is to see in a lot of the diffuse CO structures that you can kind of see here in blue, is there any dense gas that's associated with that within the galactic bar dust lanes? And so we did detect ammonia in both of our studies. So here's the gas component that's associated at the edge of the bar. We also had observations that were targeting towards the midpoint of the bar that we were calling it. So that's about this region right here. And we detected numerous dense clumps in this region of the galactic bar dust lanes. So looking at the ammonia 1,1 through 3,3 transitions, because again, we targeted just the lower transitions of ammonia, you can see that there's a lot of dense gas, there's a lot of dense clumps, and several diffuse structures throughout the region. So there appears to be a lot of dense gas associated with the CO emission of gas that is falling into the central molecular zone or being accreted into the CMZ. So there's a lot of dense gas that could be capable of producing stars in this region as well. All right, so using our observations of ammonia, one of the things we wanted to look at was the kinematics. So since these are spectral lines, you can get an idea of what the velocity, what the kinematics are doing at these 2 locations. And so this is what we see, is that towards the edge of the bar, we're seeing these very narrow line profiles of the different gas components. And so the 5 different lines that you kind of see down here that you don't really see in the 1,1 or in the 2,2 and 3,3 are just the hyperfine structures that are associated with the lower transition of ammonia. At the midpoint of the bar, however, that is when we start to see a much broader line component. So we're seeing broader lines as you move from the edge of the bar towards the central or the center midpoint of the bar. So it seems like gas is either being more turbulent or have these broader line components or multiple line components that are associated at this midpoint of the bar. So one of the other things that you can do with ammonia is that you can get an understanding of what the gas temperatures are. So ammonia is very sensitive to gas temperatures. So by using multiple transitions of ammonia and how much you have in each of those different transitions, you can see what temperatures you would need to excite some of those higher transitions. So what we found is that gas towards the edge of the bar tends to have a lower gas temperature than gas towards the midpoint of the bar. We're seeing much warmer temperatures by this point. And so there could be this increase in gas temperature as you move along the bars or transversing the bar towards the galactic center. However, with only 2 data points, it's really hard to make any conclusive results from that. So we would need to have more observations just to see if we are getting a steady increase in gas temperature as it's transversing the bar towards the galactic center. Okay, so we've discussed gas that's transversing the bar, but now I wanted to discuss what happens at the interaction locations between the bar and the CMC. So as you have gas that's entering or accreting into the galactic center, what is happening at these interaction locations between the bar and the galactic center? So to do that, I will highlight some recent work that was done by Lauren Anderson, who looked at SAG-E, which is located pretty much right here at this interaction location between the galactic bar dust lanes and the galactic center. And so looking back at the figures that I've been showing previously, you have the position velocity diagram, you have gas that's accreting from the far side here, and you can see that right at that nexus location is gas components that are associated with Sagittarius E, which is located here in the sky. All right, so what did they do? So they looked mainly at several H2 regions that are located in the Sagittarius E complex. So there's 19 known H2 regions at this location. However, based on several of the candidates, they could have up to 60 H2 regions located here as well. So I wanted to point out as well that when you compare the location of the large-scale diffuse structures to the hydrogen recombination lines, which trace H2 regions because they trace ionized gas, and some of the dense gas tracers, so ammonia, you can see that this follows pretty closely with the large-scale structures that you would expect at this nexus location. So when they were looking at gas that's associated in the Sagittarius E complex, you can see just how many H2 regions they detected towards this location in the galactic center. So there's numerous known H2 regions along with several candidates and radioquiet sources. So there could be up to 60 H2 regions or over 60 H2 regions associated at this interaction location between the bar and the CMZ. Now, several of these H2 regions are associated with a large molecular cloud. So that's about 3 × 10⁵ solar masses. And so that's what's shown here as the white contours, that is the molecular cloud, as traced by 13Cl. So you can see that several of the H2 regions are kind of embedded, mainly in that large structure. So as I mentioned, they also targeted several transitions of ammonia using the GBT. And so just to show you what some of those results look like, you can see the footprint of the KFPA receiver in the top corner. And all of these plus marks that you can see on this figure are showing their locations that they targeted in their ammonia observations. So they targeted the 1,1 through 4,4 transitions, and they have detections in most of their regions, at least in the 1,1 transition. At the 4,4 transition, they actually only detected that line in only one of their pointings. But they did cover a large portion of the Sagittarius E complex. So similar to what we did with gas that was transversing the bar, you can make measurements of the gas temperature using ammonia, which is what they did in their paper as well. And interestingly, even at this interaction location, they're measuring similar gas temperatures to what we observed in gas that was transversing the bar. So they didn't actually see any increase or similar gas temperatures to what they would observe in the galactic center, which is typically around 50. But they are seeing similar gas temperatures to what we observe in our ammonia studies as well. Now, one of the things I did want to point out about ammonia is that because we are observing the lower transitions of ammonia, which typically are fit with a cooler gas component temperature, in order to identify if there is a warm gas component that's associated with some of these cores in the clouds, you would need to have the higher transitions of ammonia to fit some of the higher gas temperatures that could be in this region. So I'd like to point that out, that typically, if you're observing the lower transitions of ammonia, typically those are fit with a cooler gas component. And so you really would need to detect or measure some of the higher transitions of ammonia just to see if there is a warm component to these regions as well. Okay, so moving on to the second part of my talk, where I wanted to discuss gas that's in the central molecular zone. So gas that's in the CMZ, just to kind of cover some just general properties of gas in this region. Typically, gas in this region has higher densities, so about 10 to the 4 to 10 to the 5. Hotter gas temperatures, so as I mentioned, you have warmer gas temperatures in the galactic center. So typically these are about 50 to 300 Kelvin. And usually that varies just dependent on where you're looking. So some of the dense clouds that you have typically show some of these cooler gas temperatures, whereas if you're looking towards some of the star forming regions like Sag B2, typically you can get up to some of the hotter gas temperatures in the galactic center. Several of these lines that have been observed towards the galactic center show broader line widths, about 10 kilometers per second on the few parsec size scales. And so based on these properties, the CMZ is thought to be a local analog to high redshift galaxies. So this ties it back in to my first slide, where I mentioned that we aren't really able to observe some of these gas properties in these distant galaxies, especially at very high redshifts. And so by studying regions like the galactic center, you can observe several of these clouds on the sub-parsec size scales. All right, so I also wanted to discuss a little bit about star formation. Can't really talk about the galactic center without discussing the star formation. And so, as you can see on this figure here, there's a lot of dense gas that has the capability of producing stars. So there's 10 to the 7 solar masses of dense gas that is a reservoir to produce stars. However, despite how much dense gas you have available, the star formation rate is actually relatively low. Typically, we're observing a star formation rate that's about 0.1 or so solar masses per year, where based on how much dense gas is available, we should be expecting a factor of 10 higher than this. So one of the leading theories behind why the star formation rate is so low is that star formation in this inner region is just episodic, and we're just looking at a low point in the star formation rate, and that it just increases and decreases as you go through time. So what could be causing this episodic burst of star formation in the CMZ? So there's two leading theories. The first one has to do with accretion. And so this accretion would be from the galactic bar dust lanes. So in this figure that was shown in Fermi and Barnes 2019, basically they measured what the amount of gas is in and along the galactic bar dust lanes, along with how long it would take for that gas to accrete into the galactic center. So that's what the figure is showing, both at the top and the bottom. You can see that it's measured by its the time till infall, along with what the rate is, and then the total mass that is being accumulated into the CMZ. So you can see that it fluctuates over time. So you get some regions that have very dense clumps, have a lot of material, and then you have other low points in your accretion rate. So the accretion across gas into the CMZ fluctuates over time. So it's not uniform as it flows into the CMZ. So That being said, if you had a large amount of material that was recently dumped into the galactic center, you could have this situation that we're observing now, where you have lots of dense gas but very low star formation because that gas just hasn't had time to collapse down and form stars. So that is one of the leading theories, is just the accretion rate from the galactic bar. The second one is quenching, and I'll talk about that in a little bit more detail when I get to discussing star formation in the galactic center. But essentially, it has to deal with the fact that as you have these massive stars, they blow out the material that's around them and can therefore quench future star formation until that gas has time to collapse back down and form more stars in the future. Okay, so for the CMZ, I'm going to focus mainly on the inner 200 parsecs or so. So typically, the region that's shown here, which is the twisted ring, is typically defined as the CMZ, which is the inner 200 parsecs. All right, so since this is a colloquium talk at a radio observatory, I cannot show the galactic center without showing the radio data. So this is one of the nice figures that was constructed by Adam Ginsberg, who looked at radio, microwave, and infrared. So radio, meaning you're tracing the H2 regions in magnetic fields. So you can see a lot of these diffuse structures, which are the H2 regions, and then you can pick up some of the magnetic fields. So that's, for example, the radio arc that's shown here. The microwave, so that's 1.1 millimeter continuum, that's the dust continuum, typically traces a lot of the dense clouds that are throughout the region. And then infrared is mainly tracing a lot of the PAH emission throughout the galactic center. So one of the nice things that you can kind of see in a figure like this is that the twisted ring structure really kind of stands out. So you get this almost infinity-like shape. So you have gas that's flowing around the galactic center, and you get this kind of twisted ring, is what we tend to call it, or the 100 parsec ring. Okay, so since most of my talk has been on orbital motions or gas motions, I'd like to touch upon some of the gas motions that we observe in the CMZ. So one of the leading theories on the connection of individual clouds to the larger structure was a paper that came out by Diederik Kreutzgen in 2015, where he presented an orbital model of gas streams relative to different clouds that are associated with the galactic center. So that's what this figure up here is showing, is the data points show the individual clouds that they use to make their measurements, whereas the continuous line is the orbital model stream of what their model is showing. So you can see how it compares to the observed data relative to what they are suggesting that the orbital stream is doing. And they've since broken it up into four streams, color coordinated in the top corner, just to make it easier to refer to different clouds along with the stream that they're associated with. Okay, so just a little bit of background about their orbital model. So they argue that the gravitational potential is axisymmetric and flattened. So how do they know this? Well, when you're looking at this plane of the sky observation of the galactic center, you can see that the reason why there's this twisted ring-like structure is because you have these vertical oscillations in the orbit. And so that suggests that the gravitational potential is axisymmetric and flattened. They also know that the gravitational potential is dominated by the stellar mass. So the stellar mass in the inner region is about 10 to the 8 solar masses, compared to the molecular gas, which is 10 to the 7 that I had mentioned earlier. And then you have Sagittarius A star is 10 to the 6. So you can see that it's really dominated by the stellar mass in this region. And the stellar mass is extended across the galactic center. So their orbital solution is an open orbit with an orbital velocity that ranges between about 100 to 200 kilometers per second, just depending on where you are and what your distance is to Sagittarius A star. Okay, so just to do a top-down view along with the position velocity slice. So the top-down view, one of the interesting things about their orbital solution is that you get these pericenter locations throughout your orbit. So that's what these plus lines are showing, is distances, the closest approach to Sagittarius A star. And so what does this mean to have a close approach to the supermassive black hole? Well, so that means that as clouds pass through, so they would be orbiting in this direction, so you have gas that's moving in, it's moving around and orbiting essentially like this. So as gas is moving through pericenter and passes its closest approach, it experiences what is known as a tidal compression. So you experience a tidal compression due to your close approach from Sagittarius A star. So what does this mean? This means that you could potentially have what's known as a time evolutionary sequence. So what does that mean to have a time evolutionary sequence? So that means that gas clouds that are associated with the same stream could show different evolutionary stages of star formation, where you have clouds that are relatively young, so haven't really spent a lot of time past pericenter, like the brick, would appear younger or would appear to basically not really have any stars or would be quiescent, whereas clouds that are more evolved or spent more time after passing through pericenter passage and have experienced that kind of triggering could show more evolved stages of stellar evolution. And so gas clouds like Sag B2, which is one of the more well-known star-forming regions in the entire Milky Way galaxy, could be triggered by this recent passage from Sagittarius A star. And so one of the things that they pointed out, because they discussed this in their paper, is that the orbital time between the brick and Sagittarius B2 is a single free-fall timescale. So you could have this triggering, and then as you move through and around the galactic center, you're basically collapsing down. So the time difference between the brick and Sag B2 is roughly one single free-fall timescale. And then just to point out, this is one of the other figures that they had mentioned in their paper. So it's just a comparison of what the velocities are doing relative. So the data points basically show what their measurements are. The solid line is what their predicted velocities would be based on their orbital model. So the velocities can range from about -100 to +100 kilometers per second. Across the galactic center region. Okay, so I wanted to paint a picture about the time evolutionary sequence. So this was a nice figure that was published by Ash Barnes, where it really shows what this means to have a time evolutionary sequence. So I had mentioned verbally about having the brick through Sag B2 being a single free-fall timescale. And so this is really what that means, is that you have a cloud that has recently gone through pericenter passage, so like the brick, and hasn't really had enough time to collapse down and form these stars. But as you orbit around the galactic center and you've experienced that triggering of the tidal compression, you tend to fragment and form these protostars until you get to Sagittarius B2, and that's where you're having this really intense star formation that's going on in this region of the galaxy. And then as you pass through Sagittarius B2 and are further along in the time evolutionary sequence, you start to get some of these more H2 regions or more evolved star-forming sites where the gas has been expelled from the regions around these hot young stars and are creating these H2 regions that you observe through, around Sag B1. And so that's what I mean when I'm talking about a time evolutionary sequence, is that basically clouds that are associated with the same stream could represent different stages of evolution. And this would be a really phenomenal result in that pretty much when we're observing in the galactic center, you really just get a snapshot. You get a snapshot of what it's doing at the moment. And so if we can pinpoint the ages between these different H2 regions and gas clumps, we can get an identifier of what gas is doing at different stages of evolution. And so essentially, you can use this information and apply this to nearby galaxies or external galaxies to really understand some of the gas properties that you can observe there. Okay, so in the last couple minutes of my talk, I wanted to briefly discuss some of the gas that's in the Fermi bubble, so gas that has been expelled from the galactic center, from the CMZ, either through intense star formation or maybe energetics from Sagittarius A star, and has been expelled into the Fermi bubble. All right, so I have to show this beautiful picture that was created by Paul Bosting, where you can really see, an artist's representation of the Fermi bubbles located above and below the galactic center, which is located here. And you can see that there's that they've identified or artistically shown several of the clouds that are associated or found to be within these Fermi bubble globes. So essentially we see, or we think that the gas looks something like this. All right, since most of my talk has been on molecular gas, I'd like to focus on a recent result of a detection of molecular gas in the Fermi bubble clouds. So there was a recent detection of 12 CO 2-to-1 in 2 of these H1 clouds using the APEX telescope. So this was a Nature paper that came out by Diatoro in 2020. So you can see that they targeted one cloud up here and one cloud down here. Again, these clouds that are being shown in this figure are the H1 clouds, and so these are the 2 clouds, H1 clouds that they had targeted using the APEX telescope. So what did they see? So in the figure that's shown over here, you can see the H1 as traced by the GBT. So you kind of see a very dense kind of region in there. And when you zoom in, and you're looking at where the contours are tracing the, again, H1, but using ACPA, so higher angular resolution, you can see that the CO, which is the color scale, really generally falls where you're detecting some of the densest H1 towards these clouds. So most of the molecular gas seems to trace the densest regions of the H1 cloud. And they mainly just targeted 2 clouds, and so several of the other clouds in the Fermi bubble could also show a lot of this CO emission embedded in them as well. All right, so lastly, I wanted to briefly discuss just how does this relate to the cycle of gas across the galaxy. So in this figure by Lilly et al. 2013, they really have this nice diagram of how gas is being transported and just recycled across the region. So essentially what you have is you have gas that is flowing into the galaxy, either through the galactic halo that's being rained back down. That essentially fills up your gas reservoir, so your reservoir that you're able to form stars. And so then you have the cycle of star formation, long-lived stars that again eject material back into your gas reservoir. And so you can have this cycle. And then you can also have wind outflows. So a lot of the high mass stars are known to have very strong winds. And so these winds can push material back into the galactic halo, thereby enriching it, which can then fall back into your gas reservoir and produce these stars again. So the cycle of gas across the inner regions of the galaxy really can play a major role in star formation and the evolution of these galaxies as well. All right, so back to step 4, and then you repeat your cycle again. So you have this transverse of gas from the galactic bar dust lanes into the CMZ and then into the Fermi bubble. And this is how you can have a cycle of gas across your inner regions of the Milky Way galaxy. And so I will end my talk there and take any questions.
All right, fantastic talk, Natalie. I particularly have to say I loved your timeline diagram. That was beautiful.
Okay.
So with that, I open up to our audience. If you have a question for Natalie, please feel free to unmute yourselves and ask away. And while everyone's figuring that out, I have a question for you actually. So looking at your ammonia observations, those 2 positions.
Yep.
You mentioned that the one region had significantly broadened lines. And I noticed particularly that across the different transitions that you observed, they get increasingly broadened. Is that a temperature effect?
So at least with the 1-1 transition, because you have pretty broad lines, the hyperfine structure that you get in the 1-1 line, like you can imagine if you had a broad line here, if each of these were broader, you would produce a very broad component, at least in the 1-1 transition. Okay. Now with the higher transitions, the hyperfine structure is detected when we were doing our gas fitting, but we basically did our measurements just using a single Gaussian component, using the Python program PySpeckit, and what we found is that gas at the midpoint typically had line widths that were around 6 or 7 kilometers per second, whereas gas at the edge was about 1 kilometer per second. So they are broader when you do fit the gas components themselves.
Okay. Yeah, it seems like you're not quite resolving the 1-1 line.
Oh, yeah.
Hyperfine lines.
Yeah, no, those are all blended, at least in the 1-1 transition. So if we went down to smaller size scales, like if you're looking at the region here, if we ended up doing either higher angular resolution or higher components, we might be able to resolve some of the individual components, which could be producing those broad lines that we're observing. But in order to just do a simple comparison between our two lines, we essentially took a single region that was the same size and measured what the gas was doing towards the brightest regions in both of those, just to make sure we were comparing the same things.
Okay, perfect, thank you. All right, and are there any questions from the audience? A question from Will here.
Thanks, Natalie. You showed some nice observations linking the dust lane to the CMZ. Are there any complementary observations that could potentially link the CMZ to the Fermi bubbles that might show some transitional gas there?
Yeah, so I mean, there was the really nice image that came out from Meerkat. So I didn't end up showing it in this talk, but when you look at the Meerkat image, which is a radio continuum image, and you're looking at maybe a degree above and below, so a little bit closer in, you do see these radio lobes that extend above and below the galactic center as well. And those seem to be connected almost to a lot of the non-thermal filaments of the magnetic fields that we observe in the galactic center, which could be, funneling material or something. I myself haven't really looked into that too much, but that might be a good place to start, would be looking at the Meerkat image or looking at gas that could be around those radio lobes and just see if maybe that could be a connection point between those two.
Cool.
All right, we've got a question from Jay.
Yes, fantastic talk, Natalie. Could you go over once again your comments? Like, I sort of missed it on the connection between the available dense gas and the star formation rate in the galactic center.
Yeah, so this line here where we're looking at the reservoir of dense gas and then the star formation rate. So is your question about how we identify what the star formation rate is, or is your question like why is it so low, or
yes, why is it so low?
Why? Okay, so the main leading theory, so basically we observe how much dense gas we have, we can count up how many protostars and compact structures that are forming these stars in order to get the star formation rate. And so really the main question comes to is why the star formation rate is so low in the CMZ. And so the main leading theory behind that is that right now what we're looking at is just a lull in the star formation rate, and that in the next, say, maybe few million years, we're going to get this intense burst of star formation in the central molecular zone. So it's not that these dense clouds aren't going to be producing stars, it's just that they haven't had a chance to produce stars yet. And that's really the main point, is that it's just a lull in the episodic star formation rate in the galactic center. And so the two leading theories behind why it's so low or why it could be episodic, the first one being that accretion rate. So basically, if you look at how much gas is flowing into the galactic center, you can see that if we had recently dumped a large amount of material, maybe 10 to the 7 solar masses, then that could account for how much we observe in the reservoir of dense gas and it just hasn't had time to collapse down and form these stars yet. And so that's one of the leading theories, is that you could have this amount of gas, a large amount of gas, that was just dumped into the CMZ, and it just, in the next few million years, we probably will see like a dense or a intense amount of star formation going on, because there's this large reservoir. It just hasn't had a chance to get to that point yet.
And so if the way I interpret this figure is that around 5.5 million years ago, there was also a burst of star formation, or is that into the future?
This is into the future. This is basically,
okay.
if you're looking back, let me get back to their figure. So so when they're looking here, you get basically a large amount that's being accreted in within the next, I guess, million years or so. You're going to get a large amount that's accreting into the galactic center. This is that one that you were talking about that's going to be accreting. Yeah. So then this one's going to be the one that's accreting in maybe about 5 to 6 million years, and then you're going to have another kind of relatively high burst, around 10. And so it almost seems like it's every 5 million years you get this kind of dumping of gas that just hasn't had a chance to form stars yet. And that's kind of at the point that we're at right now, where we see a lot of dense gas. It just hasn't had time to collapse yet.
Yeah, that's very interesting, because we seem to be finding some evidence in the clouds and trained in the Fermi bubble for episodic behavior, which would be very very tentative right now. Yeah. Thank you.
Yeah.
All right, that was an exciting question. Thank you, Jay. And anyone else in the audience feel like asking Natalie a question? Feel free to unmute yourselves. Oh, I guess another, not a huge question, but something I was noticing is, particularly in these diagrams, it seems that the redshifted gas is, the gas in the bars is asymmetrical, but the redshifted gas is much less extended. Is that just an observational effect?
Yes. So basically, if you're looking at the orientation here, you can see that your angular size for the far side of the dust lane is going to be much smaller than what your angular size is that you're observing for the near side. So it's probably just a observational effect of our orientation where we are at the sun relative to the orientation of the galactic bar.
Okay. And do you know if there are any studies, do you see the same timeline of effects in the far side as you do in the near side?
So we only targeted 2 locations on the near side, mainly just because of like the orientation of the galactic plane, where the galactic center is located relative to the GBT site. Since we wanted to basically target as much of our survey as possible. That's why we wanted to use the KPA receiver, which is good for mapping. We wanted to essentially target as much of the region as possible. Now, when you're looking at the orientation of the galactic plane, at least at the GBT site, the far side of the dust lane gets to very, very low elevation. So the galactic center itself only rises maybe about 30 degrees or so. So, even if like tilting it, you have a really low declination for the far side. So that's mainly why we chose to look at the near side of the dust lanes. I think we, potentially could go with ACA to maybe target some higher angular resolution observations for these. But really, we wanted to fill in our survey of basically mapping across the entire galactic bar dust lanes to identify where these clumps are located. So that way, we're not just doing a fishing survey with ACA or the BLA. The GBT is perfect for mapping larger structures, and so that's really why we wanted to use the GBT first, is to identify where these are located. And then we can go through with a higher angular resolution and see if some of these break up into individual clumps, or to see what the kinematics are doing, or if they have multiple components. And so I think there's quite a ways that we can go with this project. We're kind of really on the cusp of it.
All right, sounds fantastic. So I'll give one more shout out to our audience, both physical and virtual. If you have any questions, speak up now. But if not, then I would like everybody to give Natalie one final round of applause. Thank you so much for being here, Natalie. And thank you all for attending our hybrid meeting. Next week, we'll have a fully virtual talk by Eric Koch. So hope to see you all there.